These are the three kinematic equations. Likely ingrained into every AP Physics student's memory by now, these equations are very useful for solving one-dimensional kinematic problems. But have you ever wondered where these equations come from? Why do they work? The answer is calculus. Let's start with what we know about graphs. We know that the slope of a position versus time graph is equal to the velocity, and that the slope of a velocity versus time graph is equal to the acceleration. We also know that the area of a velocity versus time graph is equal to the change in position, and the area of an acceleration versus time graph is equal to the change in velocity. Let's look at an example. A 1 kilogram block is moving at a constant speed of 3 meters per second along a frictionless surface. A constant force is then applied in the opposite direction of the block's motion. We have a graph of the block's position versus time from the moment the force is applied. How could we find the velocity of the block at any given point in time? The instantaneous velocity is equal to the slope on the position versus time graph. We could use Newton's second law to solve for acceleration by plugging in the force and mass. Then we could use kinematic equation number 2 and solve for velocity. But what if we didn't know the magnitude of the force? What if we didn't have any kinematic equations in the first place? We would find the slope by taking the derivative of the function. Once we have the derivative, we could find the slope anywhere on the graph for any point in time. What is a derivative? A derivative in mathematics is the rate of change of a function with respect to a variable, the variable in this case being time. This is just the formula to find the average rate of change, or slope, between 2 points that are infinitely close together. The denominator could be written as x plus h minus x, but the x's cancel, leaving us with just h. This animation shows the slope between points x and x plus h as h approaches 0. Although this equation works for all functions, finding the derivative this way can be tedious and time-consuming. Mathematicians have found other shortcuts and rules to find derivatives faster. This is called the power rule. It is most useful for deriving polynomials, which is what we're most commonly dealing with in physics. Let's go back to our example problem. Because there is a constant force, we know that there is a constant non-zero acceleration. So our position graph is a parabola. Looking at the graph, we can find points and solve to find a function that represents the graph. Now that we have an equation for the position, we can take the derivative and get an equation for velocity. We can even derive it again to get the equation for acceleration. Notice the acceleration is just constant -6. If you were to use Newton's second law to solve for the acceleration, the 6 Newton force would equal the 1 kilogram mass times the acceleration, which would be negative because the force opposes the initial motion. Now let's take a look at the second derivative, or our velocity equation. Does it look familiar? If we switch around the values, it matches up perfectly with our first kinematic equation, where x equals time. We know from the problem that we had an initial velocity of 3 meters per second, and we could solve acceleration to be -6 meters per second squared. Let's look at another example. Here a man releases a basketball from rest 2 meters above the ground. If we want to find the time that it takes for the ball to reach the ground, we would use kinematic equation number 3. We could plug in our values for change in position, initial velocity, and acceleration. Because the ball is in freefall, we know that acceleration due to gravity is 9.81 meters per second squared if we choose down to be the positive direction. But how could we solve this problem without the kinematic equation? Once again, the answer is calculus. But this time, we are starting with only the acceleration. We will need to take the antiderivative to find the equation for velocity, and again to find the equation for position. If we go back to our graphs and their relationships, we previously found the derivative to find the slope of a graph. Now going backwards, we need to find the area under the curve, which is called the integral, or antiderivative. Because the acceleration is constant, the area is just a rectangle. However, to integrate the function, you can basically just do reverse power rule and add a plus c. So starting with our function for acceleration, we have a equals 9.81. The antiderivative, or velocity equation, would be equal to 9.81t plus c. To solve for c, we then solve the equation at a point. For example, at time equals 0, the velocity also equals 0. Therefore, c equals 0 and can be ignored. The second antiderivative and position equation is 9.81 divided by 2 times t squared plus c. Once again, we can solve for c by plugging in a point. We are considering the positive direction to be down and the zero line at the ball's initial position. Therefore, at time t equals 0, position, or x, will also equal 0, and c once again can be ignored. Let's now compare our equation for position with kinematic equation number 3. In this case, our initial velocity equals 0, and 4.905 equals 1/2 of 9.81, which is the acceleration. So once again, the equations are identical. To solve for time, the same algebra would be used, using either equation, plugging 2 in for x and solving for t. Let's take another look at kinematic equations 1 and 3. We now know that the derivative of position as a function of time equals the velocity as a function of time. And these two equations are just position and velocity equations for constant acceleration. If we take the derivative of the whole position equation with respect to t, using the power rule, it is clear that the derivative of v0 times t equals v0, and the derivative of 1/2 a times t squared equals a times t. What about the second equation? Equation number 2 is the displacement is equal to 1/2 times velocity final plus velocity initial, all times t. Remembering back to the graph relationships, we know that the area of the velocity graph is equal to the change in position. If we have constant non-zero acceleration, the velocity graph will always be a straight diagonal line, which creates a trapezoid with the x-axis. The equation for the area of a trapezoid is the average of the two bases multiplied by the height. Initial and final velocity are equivalent to the lengths of the two bases, and time is equal to the height. If either v or v0 is equal to 0, the area is now a triangle, and with only one height, the equation solves for the area of a triangle. In all of these situations, using the kinematic equations was just as fast, if not faster, than using calculus. However, being able to find and derive equations is necessary if you want to be able to solve problems when acceleration is not constant. For example, if given a problem with a vehicle that has non-uniform acceleration, such as a equals 15t, in order to find velocity and displacement, you would need to use integration to be able to solve for velocity at a given time or displacement at a given time.